Okay, we are recording now. So welcome everyone to the March edition of the World Ocean Council Ocean Restoration and CO2 Reduction CDR Roundtable. Hard to believe another month has zoomed by. And what I'd like to do here is share a screen and pull up the agenda here. I'll leave it. I always find it easier to navigate with this partial view like this, if that's okay. And so we, moving forward with things a lot, as I was saying a few minutes ago, just a lot of activity and action in the ocean restoration and CDR removal space. Sorry, carbon dioxide removal space. And we had, based on the feedback, I had really a good session last month, and the three presentations that really was the focus. That was the focus of attention. Then we had Ocean Nourishment, and we had Project Vesta, and we had Sea Combinator, and great presentations, really good discussion around those businesses and their development. And I know John Ridley from Ocean Nourishment is on the road somewhere in Australia today, so unable to join us. But you know, that really I think was exemplary of what we want to do here, is bring together the business and investment community around ocean restoration and CDR and negative emission technologies. So in continuing along those lines, we'll be having a couple of presentations today that I'll mention briefly now, but we'll first do introductions in a second. There we go. And so we have Phil Gilthil, from CEO and longtime colleague with Ocean-Based Climate Solutions, and then we have Mark Van Kates and Krish. And Krish, I won't try and do the last name. I'm sorry, I don't want to get it wrong. From ARPA-E. Apologies for that.
Easier than it sounds.
Is it? Help me.
Yeah, well, let me try saying it for you. There are so many vowels. It's Doraiswamy.
Doraiswamy. So really, as it reads, Doraiswamy. So thank you. Apologies for that. Krish Doraiswamy with ARPA-E. And so, but first, let's as we always do, those that are first timers to the event, to the roundtable, or have been here but not introduced themselves previously, just to give introduce yourselves with name and affiliation. And I'll just stop sharing here so I can see all the participants. But please, if people want to jump in and introduce themselves, if you're new to the roundtable.
Hi, I'm new. This is Matt Elliott at OceanKind. Thank you very much for having me.
Thanks, Matt. Great to have you here.
What's your organization?
OceanKind. We're a marine conservation funder.
Great. Thank you.
Anyone else? I guess so. The good news is we've got some good continuity. Please, Eileen. Yes, of course.
I'm new as well. I'm very pleased to be here. I'm Elena. I'm from Denmark, and I represent a new initiative called the Great Caribbean Barrier Initiative. And so I'm very excited to listen in and be part of this today. So thank you.
Thanks, Elena. Great to have you here. And Rafa, good to have you here. This is a new group for you as well, if you want to introduce yourself.
Hi, everyone. I'm Rafa. Thank you very much, Paul, for inviting me here. I'm representing WOC Veritas. We are a sustainability research and consultancy firm, mostly working with investors. Thank you.
Great, Rafa. Good.
All right.
Okay.
I'll go next.
Oh, Salvador. Right. Great.
Yeah. I'm Salvador Garcia. I'm with Ocean-Based Climate Solutions. If you don't mind, I just have about a minute and 30. I just want to let you guys know phytoplankton in our. Philip's going to be talking about this a little further ahead, but I thought I'd kind of get ahead and say a little something. Phytoplankton in our oceans absorb 30% of the world's CO2 emissions and produce 50% of the oxygen we breathe through a process called photosynthesis. But due to climate change, our oceans are warming, producing less phytoplankton, destabilizing our climate and marine ecosystems. If we're to solve climate change, we must harness the power of our oceans and phytoplankton. We've developed a renewable wave energy powered pump that upwells cold, nutrient-rich seawater from 500 meters deep. Each pump can fertilize enough phytoplankton to remove 250 tons of carbon dioxide per year. And this is verifiable with biogeochemical instrumentation and at a long-term cost of under $10 per ton of CO2 removed, lasting years, if not decades. These pumps are more effective than any carbon capture technology on the market now. And best of all, they're safe because the process is natural. Photosynthesis is happening today everywhere across the globe, and particularly in our oceans. And our customers are corporations wanting to become CO2 neutral and governments looking to meet or exceed their Paris Climate Accord promises. And we're a team of engineers, ocean scientists, and climate youth. And we're looking to raise $5 million to deploy our first array of 20 pumps so that we can begin the commercialization process. And I'm sure Philip will get into more info where you could find us on our website.
I don't think I have to. You said it all.
Thanks, Salvador.
Thank you, Salvador.
All right, just checking. We had a few people who have had to sending their apologies that they wanted to be here but now are not able to. Okay, thanks everyone. Well, good to have you all here. Clyde, did you want to jump in? No, okay. Let me go back to the agenda here, and I will, as I say, we are recording, and I'm a little bit under the weather, so I'm counting on all of you to help keep up the energy and momentum here today in today's call, as I'll be stumbling a little bit foggy-headed. So let's. Sorry, just adjusting the screen here, and so let's move into these presentations. But just to catch up on the agenda here, then we'll be after the presentations, and so we want to really, as we did last time, take time for discussion around those, both immediately after the if there's key questions around each of the presentations, and then if that opens up a broader set of issues that we can take some time to get your thoughts and questions and ideas on the table. And then we'll be bringing up the development of the Phytoplankton Council, myself and Peter Fikowski, and then talking about, as we started to at the very beginning of the call, about the COP26 and ocean restoration and CDR. And then as we have time, getting back into the sort of the roundtable structure and process. And I would like to, just in terms of that, while we have everyone here, to say there is, overall, we do have a mailing list for the roundtable of, I haven't counted it all lately, it's at least 70 to 80 interested parties. And and again, the focus here, of course, for the World Ocean Council is on the business and investment community, and that we will be moving towards working out a set day of the month, so that it becomes a more easily calendared event every month, rather than a new date, new part of the end of the month each time we propose this. So hopefully that will help create the continuity that's valuable in all of this. So with that, let me stop screen sharing, and Phil, hand it over to you to pull up the screen share and your presentation and introduce yourself. So
Okay, great. Let me get my screen shared. Go to full screen here. So I'm Phil Cahill, CEO of Ocean Based Climate Solutions, and I've been at this since 2005, prompted by Hurricane Katrina hitting New Orleans. The idea came to mind of upwelling water using the big waves of the hurricane to cool the upper ocean and reduce hurricane intensity. Far-fetched idea, actually had it modeled by a leading hurricane scientist, Isaac Guinness from University of Rhode Island. And in fact, with a large number of these hypothetical, at that point, pumps, you could have reduced Katrina by half a category, which is quite a bit in hurricane language. So that was the beginning, and we've been at it ever since, looking for different applications of the technology, generating electricity, desalinating seawater, aquaculture onshore, aquaculture, pumping seawater onshore. And now we've come back to the climate change problem and upwelling deep nutrient-rich water into the upper ocean to grow phytoplankton. And the oceans, of course, are the obvious place to go. The heat uptake, according to this graph from Dr. Fei Chai from University of Maine, 93% of the heat uptake has been in the ocean. So that's where we have to go to fix the problem. And relating upwelling and warming, Professor Riebesau from GeoMar, German Marine Research Institute in Kiel, has said this to us in an email that upwelling can serve as a restoration measure, overcome the decline in ocean productivity due to water column stratification. So the warm water is getting warmer, sitting on top of the colder deep water. There's less upwelling of nutrients, therefore less productivity. And you can overcome that potentially with upwelling. So it can counteract that trend and do the restoration, as he mentions. And so this is the pump that we've been working on. It's version, who knows, number 5 at least. 1.9 meters diameter, conceptually potentially 500 meters deep, reaching down into the pool of nutrient-rich water and bringing that water up wave powered. So on each wave cycle, the check valve in the bottom opens and closes, forcing the water column up the tube. It's a heavy duty industrial fabric tube, and that's part of the key to this product is that it rolls up like a spool of fire hose on a, or whatever, on a buoy. And so it self-deploys. You drop it off the boat, the bottom heavyweight sinks. That's filling the tube with water, so it's primed with water. When the tube is fully extended, then it starts bobbing up and down, and you get the water column moving upward. So a very efficient and low-cost deployment. And then it operates autonomously for, it's free drifting out in the open ocean, as I'll show you, and operates on its own. So very efficient and low cost once you have it out there, potentially 250 tons per pump per year. And we will deploy these in what we would call the old ocean, which is the North Pacific and parts of the South Pacific. When we say old, it means this is the ocean that is less in contact with the atmosphere, or over a much longer time period comes in contact with the atmosphere. And so in terms of sequestering CO2, that's where you want to put it. You want to have it stay away from the atmosphere for a long time period, 1,000 years, 2,000, up to 5,000 years perhaps. And so the two regions that we would go to first are the North Pacific subtropical gyre, that's called an LNLC, low nutrient, low chlorophyll region, the upper ocean being low in nutrients, an ocean desert, and low chlorophyll being the signature of photosynthesis. And so there's very little productivity in that part of the ocean surrounding Hawaii, but thousands of miles each side, of course. And then the South Pacific also, now it's a little different. It's a high nutrient, low chlorophyll area. So the upper ocean is replete with the major nutrients, nitrate and phosphate, but it's missing the trace nutrients, in particular iron, which is needed to trigger the process. So that is also a potential area for this technology. The Indian Ocean is a younger ocean, and the Atlantic is much younger. And so the technology would work fine there, but the CO2 that we take down would reappear in a sooner time frame, that being 100 years, 200, 500 years, maybe 1,000 years. But it's still possible to go there, but the low-hanging fruit would be the North Pacific, the subtropical gyre, and then the South Pacific also. And so the potential we like to point out on this chart. We're now at 420 about parts per million CO2 in the atmosphere. Pre-industrial was on the order of 275, I believe. So that's how big a hole we have dug ourselves in terms of destabilizing the climate and wrecking the ocean, beginning to. And so the problem, of course, and that's what COP26 will be all about, is if you do nothing and the trend continues of burning fossil fuels, will be above 750 to 800 easily by 2100. And that will be a world that nobody can really live in. The fossil fuel phase out is going to be a huge challenge, and it's hard to imagine we'll go to zero on that. So even with, say, a 5% per year decrease, you'll still have some fossil fuel use, some CO2 emissions. So the orange line is if you phase out fossil fuels, but you don't remove the CO2 that's already been emitted, you're still above 500 to 550 ppm, which also is going to be a very challenging environment. And so you need to do both. You need to have the fossil fuel phase out, and you need to have carbon dioxide removal. We would say the ocean is the place to do that. With our technology, if aggressively ramped up in combination with fossil phase out, you'd get to around 300 ppm. So you'd basically be restoring the pre-industrial environment from that perspective. And the costs over that time come down to under $10 a ton. It does start higher, of course. And this is entirely driven by the ramp up rate and by the manufacturing and deployment efficiencies. And so this is a guide to the cost per ton for our technology. I think a safe number is under $20 a ton by 2050, perhaps $15 a ton in that time frame, and then going down, because the pumps keep working at almost no cost once they're out in the ocean. And we have to talk about the risks, of course, and another professor from GeoMar, Andreas Aschlies, very well known. He sits on the National Academy committee that is evaluating ocean CDR. And he has written to us, no environmental risk with small scale field trials. And if you go larger scale, you'll have oxygenation, cooling, enhanced biological productivity, and that includes up to the higher trophic levels, including fish. There will be shifts in the ecosystem, which is hard to evaluate at the present time, but he thinks mostly be positive. And there could be some other risks. We cannot say for sure the effect on ocean pH, ocean acidification. Ulf Rivesel, the previous gentleman we referenced, thinks the surface effect will be it won't have a big effect on the surface. In terms of ocean pH, there could be a negative effect in the deep ocean, but that remains to be seen. So our market are corporations and governments, and under corporations, we're looking for those who wish to become net zero carbon dioxide, offset their emissions, draw down their historic emissions. And our business model is a subscription model. So a corporation would come to us and say, we want to eliminate our 1 million tons a year or whatever it is, and become zeroed out by 2035. And we would calculate the number of pumps needed. And they could pay in cash, and it's not inexpensive to remove CO2 from the atmosphere, even at a low cost per ton. Or we have come up with a twist, which is stock for carbon. So there are some companies which, by their nature, have high carbon footprint and a relatively low cash on their balance sheet. And so they may prefer to pay in stock rather than cash. If they're a public traded company, we can take that stock and sell what we need to fund the program, and then our profits are in the remainder. And that, of course, dilutes the shareholders. It's free to the corporation, cash flow wise, dilutes the shareholders, but the stock markets are rewarding sustainability with higher PDE ratings. More funds are flowing into sustainable companies. And so the shareholders get their money back, free to the company. The shareholders come out with a better ROI, and the environment wins. And then, of course, the second market are governments who need to meet their promises under the Paris Accord and even ramp up those promises with higher ambition. So this chart is the green are the companies that have plenty of cash and good pay for it, and the yellow and orange are on the margin of cash or stock, and the red are companies who have a big footprint and less cash and might want to take advantage of stock for carbon. In terms of our scale-up plan, we just submitted our response to Stripe, credit card processing company, for their request for RFP for negative emissions, and we should hear in the early May timeframe if we're selected and negotiate a contract with them. We were invited by Microsoft last year and have been told we'll be re-invited this year. And so we would hope to get them on board in a project next year. And then we basically, our target is to double subscribers year by year. So 2 more in 2023, and then 4 more in 2024, and so on. And if you follow that progression, and I just looked up how do those revenues stack up against Amazon, for instance, is it a realistic growth rate? Well, it's slower, the orange line being us, in the first 8 or 10 years, and then it goes up much more quickly. But it is in the same ballpark as a growth rate seen by Amazon over the last 12 or 13 years. So here's our team. We have 6 people involved at this time in the management of the business. We have a small board of 3 people, myself, chief engineer, and our lead investor, Luther Hodges from North Carolina. And our advisory board, some well-known scientists, Ian Walsh, formerly of Seabird Scientific. They built the biogeochemical Argo technology that we'll be using to validate the tons that we remove. Dr. Fei Chai from University of Maine is one of the leaders in measuring carbon in the ocean, and the other 2 gentlemen I mentioned from Geomar. And we have our Stripe proposal funding, hoping we get that $3.5 million. We are looking for an additional $5 million this summer, sooner the better, to deploy an array of 20 of these pumps out vicinity Hawaii with the Argo, biogeochemical Argo sensors to detect the actual net export of carbon. And then our Microsoft proposal, which we would submit in the August timeframe, taking our projections and come up with these range of values depending on the discount rate and the time period and the number of pumps operating, which you can see in that table. And so that's what we are. And we have a great new website that Salvador has put together. So I invite you to take a look at that, and happy to answer questions now or in a Q&A session. I'll
Thanks.
stop my share.
Thanks very much, Phil. Well, there may be questions that want to bring up some of those slides again, but great stuff, and really encouraging to see the interest from some of the potential funders. Questions or comments for Phil?
Yeah, Phil, this is Krish Doraiswamy. I'm curious, what do you anticipate as the total number of deployments that you would expect to have installed in order to move the needle as much as you're anticipating?
Yeah, and that's a pretty much an arithmetic exercise. So we will be establishing what we call a standard factory for each of these corporate subscribers, which can produce 1,000 of these pumps a year, 4 a day for 250 days. And it would have a dedicated high-speed workboat. It can take 10 out at a time, deploy them, come back, get another 10. So that's our unit of growth, is one corporate subscriber, a factory producing 1,000 per year. And so it's additive. The second year, another 1,000, another 1,000, another 1,000. So it grows for a single corporation if they maintain their subscription 1,000 pumps a year. But then if we double the number of subscribers year by year, you get the ramp up. But to say, back on the slide, I'll just talk about it and try to go back to it. It really takes until about 2035 to move the needle because of the deep hole that we're in on CO2. So that would be, I'm off the top of my head, 100,000 of these pumps. It might be more. I could look that up and get back to you with an actual number. It's a big project. They're not all that big themselves. The buoy is 3 meters wide, basically. The tube extending down 500 meters. So they have a small footprint.
And what are you projecting as the annual carbon uptake per unit?
250 tons per unit per year. And that's based on the Dave Carl, Ricardo Letelier 2008 paper, which evaluated precision upwelling in the North Pacific would deliver excess phosphate and trigger a second bloom. So you take down more than you bring up CO2.
Thank you.
Other questions, comments? If people can just physically raise their hands. So I'm seeing CJ and Mark and Peter. Go ahead, CJ.
Yeah, thank you. Thank you, Phil. Great presentation, very interesting. So I'm based in Stockholm, Sweden. I have quite a few questions, but I'll try to limit myself to two. So being a layman in this area, my first question would be, the technical lifespan of this, and I should mention my affiliations are Verdivo Capital and the Sustainable Impact, which is an online platform for sustainability. So my first question is then about the technical sort of duration or lifespan of this. How long would it last for before it deteriorates? And secondly, I'm just thinking maybe a bit funny here, but from a personal standpoint, I'm sitting in Stockholm, in Sweden, and we have just in my backyard here, we have a sea called the Baltic Sea, which I think and many people think is in a very bad state. And we have this very small sound between Denmark and Sweden, where we're getting all this sort of fresh, oxygenated water into here. And maybe Eileen Sørensen in Denmark would know more about, but I think it's like the most 10 kilometers, this big small strait between Denmark and Sweden, that it's providing all the Baltic Sea with fresh water, basically. So and I'm thinking about the necessity. My second question regards the necessity of currents, and not sure I know a lot about that, but what you mentioned here in the Pacific, and my question is, to which extent are you totally depending on strong current situations, like here in this very bad state, but the Baltic Sea, for instance, is what kind of currents do you need to have an effect? I know it might be a complex question that is we don't have time for now, but could you just comment on that and the use in sort of lower current environments? Thank you.
Yeah, on the durability, that's a great question. And we have engineered this, and we build into our cost structure a RR&R, Renewal, Refurbish, Repair, and Replace Fund. And that is a substantial amount of money. So as we have these boats out, they'll be able, if there's a unit that's not working, whatever, we can haul it up, either bring it home or maybe fix it on the boat. The component most subject to failure is the fabric tube, and it's a very heavy duty truck tarp type material. One of the many benefits, they can make it in any length that we ask. So there are no seams other than the vertical seam. We take 2 panels and stitch them together edge to edge, and that gives us a tube. So we think that could last 80 years. There might be some interim maintenance. There will be some biofouling, but probably not on the fabric, which is a silicon coated. There'll be some biofouling on the surface buoy components. And so again, that's a maintenance issue. Haul it in the boat, scrape off the barnacles. In terms of the Baltic, of course, we are wave energy powered, not current powered. So that's different. but we do need waves averaging, we'd like to see, and we would see it in the Pacific, 2 meter waves at a 12-second period, something like that. And that's gives us a basis for estimating the 250 tons per pump per year. If it is less wave height, then of course you'd have less upwelling. There could be an application in the Baltic for stirring up that environment. You have all the problems that you've alluded to of the pollution and the fresh water and the so on and so forth, stratification. And so there could be an application there. It wouldn't have to be the 500 meters, of course. You can make these in any length, but it is amenable to that. So I hope that's answered those immediate questions for you.
Great, thank you very much.
Thanks, thanks, Phil. We'll jump over to Mark and then Peter.
Yeah, Phil, thank you very much. I was just curious about your validation strategy. We have been really looking a lot more at ARPA-E at very much at terrestrial parts, but what we have experienced there is that validation is really the crux of the matter, especially when you are hoping to obtain higher degrees of revenue. And so really showing that it's not just a model-based system, but actual validation, and then in particularly also validating that the pumps are working. So how are you going to equip them with iridium and like phones to give out notifications? So it's just a question really, how you're making sure when you have hundreds of thousands of these, are you just assuming that, well, 10% won't be working and you give a discount, or?
Yeah, great question. Each pump will have a GPS and a satellite uplink, as well as a temperature sensor at the outlet, just 15 meters or so deep where the cold water comes out. So if we do not see any cold water, then we know that pump is not working, and we know its exact coordinates location. We also are going to heavily rely on the biogeochemical Argo units that have just come out. And these are the robotic floats that sink down 2,000 meters and then rise back up through the water column, hit the surface. They've been measuring the ocean chemistry on the way up, and they uplink that data to the CLS headquarters in France, and it's public data. So we will employ one of those. We're thinking right now for every 20 of our pumps. Our pumps will be spaced, we think at this moment, 2 per kilometer, so on a diagonal, so 700 or so meters spacing one to the next. And there's been some great work by Dr. Fei Chai from University of Maine with the biogeochemical Argo that if you do daily sampling with that technology, you catch all the phytoplankton blooms that are happening. Whereas if you do a 5-day or a 10-day sampling, you miss a huge amount. And he's actually calculated a value of 8.9 grams per square centimeter, or whatever the unit is, for daily sampling, and only 1 gram measured in 5-day and none on a 10-day sample. So we will use daily sampling of those Argos. Now they have a battery life that's limited to about 200 up-down cycles. But there's another technology working on the OTEC principle, a company called C-Trek out of California, and they make a miniaturized ocean thermal energy conversion power pack, and they have attached it to the biogeochemical Argos, and they essentially can power it forever based on the thermal capabilities of that power pack. So it adds cost. The biogeochemical Argo is 100,000, and adds another 50,000 to put on that power pack. But if you get unlimited life and daily samples, it works. And so that would be our primary validation, is to measure all the time at a very high resolution, 1 per 20. We can probably expand that as we get into the program of one of those per 100 pumps maybe, but for starters, 1 per 20.
Thanks,
And
thanks.
and then just
Sorry,
a
go
quick
ahead.
follow-up, the validation is then that you are pumping the water and that you get phytoplankton bloom. But that doesn't really speak to sequestration yet. Do you see that as a need for validating the sequestration that actually happens?
Well, that's the biogeochemical ergo. So it's measuring particulate organic carbon, for instance, as well as all the other chemical attributes that are important in the equation. I'm not an ocean biogeochemist, so I can't speak on all the technical details of that, but I think it's pretty readily available information, and I could send you Dr. Chai's a couple of his slides, perhaps, if you'd like.
That would be great. Really appreciate that. Thank you.
Yep.
Great, thanks, Mark. So we'll go to Peter, and then we'll go back to Mark and Krish for the ARPA-E presentation. Thanks. Go ahead, Peter.
Phil, great presentation. I love the idea. It's nice and simple. What would the business model be for a government? So if a government said, "Oh, this is worth our doing," how, in a nutshell, how would the finance work?
Yeah, they would have to pay in cash because they're not a stock, publicly traded stock corporation where there's not that option. And so it would be a subscription business model. They have a Paris Accord commitment or promise of X tons, and they're not there. So they need to add additional tons to what they're drawing down, and they would have to subscribe to the number of pumps. And we, again, like to go in a full factory commitment of 1,000 pumps a year. Factory-wise, that's like 20 people in a supermarket-sized building. So it's a very doable. Port cities all around the world that are adjacent to the appropriate oceans.
Thank you.
Okay. Thanks very much, Phil. And I'm sure there'll be more points that come up today and as we move forward overall with this and how it relates to some of the other businesses that are under development and the overall pathway in terms of nutrient enrichment and phytoplankton and moving water from one part of the ocean profile to the other. Let's go over to Mark and Krish with ARPA-E and get caught up on what's the important work going on there in the MARES program. So Mark, over to you. And if you want to go ahead and share screen.
To make sure, is everybody seeing the
Yep.
full screen that you should see? Okay, very good. First of all, thank you very much, Paul, for the opportunity to present here and to everybody for listening. Wanted to start out with a quick overview of ARPA-E. I think some of you may know it, some don't. We are a part of the US Department of Energy, dedicated to funding research and development for high risk and high reward transformational ideas. Really, the tagline is changing what's possible. And really change how we get, use, and store energy, and ultimately accelerating energy innovation. The agency has been around for a little over 10 years right now. During that period, we have spent about $2.6 billion on a little over 1,000 projects. One of the measures of success is that we follow the money with regard to follow-on funding that these projects receive, and there's about nearly twice as much in private sector follow-on funding. There have been quite a number of companies spun out or arisen from ARPA-E projects, and clearly a lot of scientific work with peer-reviewed papers and a good portfolio of IP. The way we have been spending the money is mostly through focused programs where we are trying to bring really the cutting edge players together, but we also have a number of open solicitations. And in that context, I may just put a quick plug in for people that haven't heard of it yet. We currently still have the Open 2021 solicitation out that is closing for its concept papers on April 6th. But what I wanted to highlight here, so we really are operating all across the energy landscape, but we have a few things in the ocean. So the Mariner project program that I'm going to talk about a little bit more is clearly one of the ocean efforts. The Atlantis program is on offshore floating wind technology. And then we just launched the Shark program, which is on marine hydrokinetics. And we have also been working on a number of factors in carbon dioxide removal. Once again, on the terrestrial side, we still have a program called Roots that looks at increasing soil carbon sequestration, and then Flex is more combining power plants with carbon direct air capture. But we also are pushing more and more into the ocean for CDR, and we just funded 3 projects in starting last fall that look at various aspects of direct CO2 removal from ocean waters. And you can find more details on that on our website. I just wanted to make you aware that there's efforts going on exactly in that space right now. But what I wanted to talk primarily about is the RPE Mariner program. It launched in 2016, has over 20 projects, and we spent a little over $50 million on it so far. But before I go into more details, maybe a quick overview of what motivated us. And really the starting point was less purely CDR and climate change per se, but really the need for more energy and more food by 2050 to take care of, by then, what will likely be around 9 billion people. And so in all cases, what you really want is biomass is really a critical component here. And it's been shown to be highly flexible for low carbon energies. It can be used as a fuel, it can be used as a biogas for providing heat. And so it's really, really flexible. The problem with biomass has always been that we have a direct competition with terrestrial agriculture, and you can't expand it on land due to limitations of good soil that's available and clearly fresh water, and you don't want to push into the last preserves of real high quality nature areas. So at the same time, the US has a tremendously large US EEZ that is one of the largest in the world with abundant light, water, and nutrients. And so it's really the idea that if we can figure out how to tap into that, it could be a very interesting part. And then finally, I think as we're pushing along, we really look very closely also at climate change. And so, and the opportunity to use macroalgae to capture CO2. And here's just a few basic calculations, but on a very rough level, 1 ton of CO2 so 1 ton of dry macroalgae has captured about 1 ton of CO2. And if we are going after the primary units that everybody has been looking at as 1 gigaton, and there's the optimistic scenarios, we will still need about 182,000 square kilometers. It's a big number, but it's 1.6% of the US EEZ, so it's not completely outlandish. But nonetheless, this is just from a multiplier effect, this is nearly 300 times more than what is currently produced all across the world in macroalgae. And so that's where really the Mariner program started to set in, that it's very much a scaling issue. Ultimately, we have to get the costs down, but at the same time, we have to really get the scale up. And so the program was designed to really address some of these key challenges that will have to be encountered when you expand cultivation into offshore waters, making sure that you reliably access deep water nutrients, because you can't just rely on naturally upwelling nutrients. And then, since it's an energy technology, you need to be very efficient in harvesting and the biomass transport technology to get a good energy return on investment. And then in the end, from a cost side, you really need to increase the productivity on the individual plant level and on the entire cultivation system level. And so we developed a set of core metrics. Once again, we want to push for large scale type systems, but we also want to make sure that these are not niche solutions. So we have been asking all the teams to make sure that there's enough area where these can be deployed. The target on the cost side is at or below $80 a dry metric ton. And as I mentioned before, the energy return is supposed to be at least 5-to-1. So overall, we have been taking a 5-pronged approach. At the core of it is experimental deployment of cultivation and harvesting systems. So it's really an integrated, so looking at a variety of geographies and a variety of species and a variety of systems. But we felt that in order to accelerate and support this effort, we were looking at funding a number of tools as well. So it's just in one case here, this is an additional very highly energy efficient transport vessel. We also felt that modeling is absolutely critical to reduce the number of experimental iterations that you have to do in the ocean, so we can learn a lot more on the computer, and not just with regard to mechanical robustness of the system, but also with regard to nutrient fluxes, because these are basically large farm systems and nutrient supply is absolutely critical, and flux of nutrients through these farms is being modeled as well in order to make sure that they are productive across the whole area. Once again, further offshore, you need capabilities to monitor the farms, and we have been looking at underwater and aerial monitoring capabilities with either hyperspectral sensors, optical sensors, or sonar acoustic sensors in order to monitor growth and potential for disease. This is definitely still under development. And then finally, we have a category that is focused on breeding and genetic tools, because one of the things, if you look at terrestrial agriculture, there have been enormous gains made over a period of nearly 10,000 years, first through just selective breeding, but that process has been tremendously accelerated with genetic information. So we are actually have been funding projects to build genomic maps of critical species, and then looking at something that's called genome-wide association studies, where you can look for markers that help you find out which genetic traits are associated with the desired phenotypic traits. And you can accelerate the breeding process without even having to do any genetic engineering in that space. And so this has been going quite well right now. We have been doing this for Saccharina and for Macrocystis, but we see it more as a basis from which people can expand into other areas as well. The other part that's really, so these are more the core technical categories, but we very early on recognized that you really have to have also a spatial planning component, and we have been working very closely with NOAA to identify areas for deployment of these potential future farms. And it's, on the one hand, just to identify what are good areas from a physical and biological point of view, but you also have to look at where are potential conflicts with other ocean users. As James Morris from NOAA always says, the ocean is a pretty busy neighborhood. And so the planning tools have been absolutely crucial. And right now, there is a tool set for the US out there called Ocean Reports that some of you may already know, which is really the opportunity to draw a little geometric shape of any area in the US EEZ, and you get basically all the data that are, it's like several hundred layers of data, all from geographic data, physical data, biological and chemical data, as well as are there military uses, are there industrial uses, and it really gives you a fantastic overview and helps you in planning and in permitting. So and right now, so these are the parts that are critical for really just growing the material. But then in order to grow an industry like that, you ultimately have to ask yourself, what are we going to do with this material? And so that's where we have drawn up really a landscape for potential uses of seaweed biomass. Some of these are clearly already done today. It's like directly eaten as food. 55% of current production is actually going straight into that space. Hydrocolloids, over 40%, like carrageenan, agar, alginates are another component. But there are emerging opportunities for animal feed, alternative proteins, and biorefineries. And one of the areas is really carbon capture. And if you look at it from a market size, that might be really the largest. The price at this point, on average for voluntary commitments, tends to be more in the $8 per ton range, which is very clearly below what we are currently able to match from a cost perspective. But if we're talking $50 a ton, we get much closer to that target. So that's something that is definitely something we should keep in mind in that context. And what we have to think about in the carbon capture context then is really where do we go in order to sequester the material? Capturing is one thing, but it can be very quickly fed back into the atmospheric or the global carbon cycle. So you really need to think about how do you transfer the material into more long-lived pools. And so there's three categories that we have been looking at, and I'm going quickly over those. So there's first a cultivation-associated carbon sequestration, meaning that there's a certain percentage of the material of the primary photosynthesis transferred into either material that is excreted or material that breaks off and then translocated into either the sediment or deeper ocean parts where it then gets contained. The exact number of this is still a matter of debate. There's an interesting study going on right now by Ocean 2050 that is looking to assess in various existing seaweed farms how much carbon is sequestered there. But it is definitely something that no matter what you afterwards do with the material that you harvest, this is kind of a baseline carbon sequestration potential. The other thing that has been very popular that people are looking at a lot is purposeful deep sea sinking of seaweed, where you are really taking material that you have purpose grown, then harvest and then sink it into, again, the deep ocean with the purpose of sequestering it for an extended period of time. It reduces transport requirements. It has the potential of putting the carbon away for hundreds and potentially thousands of years. However, we don't really fully understand yet what this would do to the ocean floor ecosystems if you do that on a very large scale. And we also don't generate any product or revenue opportunity if we take the whole plant and bring it down. So this is definitely still something that needs significant evaluation, but it's an area that could potentially be relatively easy to do. Finally, there's more of an integration with the biorefinery that I mentioned earlier, and the BECS stands for bioenergy with carbon capture and sequestration. And in that case, you would take the seaweed, put it through an anaerobic digester, which produces a biogas, which is a mixture of methane and CO2. And then you can separate out the CO2 and sequester it. And then in a second step, take the methane to use it in, for example, a gas-fired power plant or some other process where you can do additional carbon capture and then store it as well. It even then allows that you can extract higher value materials up front, or also sequester significant quantities of fertilizer. Just if we take a gigaton, we would have very, very significant quantities of fertilizer that are on the order of the same amount of nitrogen that we use in all of the US agriculture system. So there's some really interesting opportunities in that space. And what we felt was necessary to overall still evaluate that is that you look at it from a carbon impact perspective and basically an LCA system. So we engaged the Argonne National Labs GREET team to really assess, build a model for macroalgae. They have done that for a lot of biofuels and bioprocesses so far. And so we are, and our teams are working with ANL to build these modules to get a proper understanding what is really the overall LCA, and particularly with regard to carbon dioxide, to make sure that we overall, with any solution, have a positive impact. So overall, the big challenges are still across a range of things, some of them scientific and technical. So we really have to validate the long-term carbon outcomes. And we also have to really develop the right processing methods. And there's still ongoing efforts in just the production and cultivation. So these things are really having to continue to go on. It's really critical in order to achieve economies of scale. This is in the whole supply chain, and then developing the necessary stepping stones in the marketplace, because we really need to have a pull on the development of the technology. The regulatory part we have to pay very close attention to, and at the same time, as the industry grows, social license is very critical to maintain. So far, there's been a lot of positive social license news for seaweed, but as we increase in scale, we want to make sure that this is maintained. So we believe that really collaboration across diverse stakeholders is very critical to achieve these goals. And we have been working and reaching out to a whole host of stakeholders. And I think this is really an area that we hope will grow overall. And it's really something, while we are overall US centric, we definitely have an interest to work with leading organizations around the world, because we believe that it's, in the end, it's a global opportunity and we need global collaborations on this. Don't know that I need to really go through this in a lot of detail. The one thing I wanted to, just in our own sense, we always are looking for program directors and technology to market advisors like Krish to help us advance program ideas across the whole energy space. The role that Krish and I are filling are time limited. We are on our way out, but independent of our direct areas of engagement, we always are looking for new people, and if we can convince people with an interest in the ocean, we definitely want to encourage them to look at that. If anybody is interested, just reach out to me, and you can find more information on the website. And the final thing is we have our RPE Summit coming up 24th to the 27th of May. It's going to be virtual. That means no travel required, and you have the opportunity to participate from anywhere in the world. So with that, thank you very much, and happy to take any questions.
Great, thanks, Mark, for that really rich and thorough presentation of the situation there. So let's open the floor up, and particularly to think about where the RPE effort and the Mariner program, and whether there would be other programs in the future potentially, but how that relates to enterprise development and commercialization, and linking with both the businesses and the investment community, which in your last slide clearly showed the scope of the interactions, and certainly how to think about how we can collaborate from the World Ocean Council side, as you and I and Chris have started to discuss in a number of calls. So questions or comments for Mark and Chris? Let me go back to full screen here so I can see.
Yeah,
I see Peter.
I can close this here. So
yeah, so we can see everyone.
Yeah.
Great.
Yeah, this is Krish. If I may just.
Oh, please, Chris. Yeah.
Yeah, just to make clear something that I think was implied in Mark's slides, but bears pointing out. All of the work is actually done by teams that we are funding. Our funding of those teams is time limited in that once they have demonstrated their concept and taken out a lot of the early stage technical risk, the further implementation of their technologies depends very much on their ability to generate follow-on funding from the investment community and others. As Mark mentioned early on in his presentation, a large part of how we view success is the extent to which the startup companies we are funding or the academic teams we are funding are actually able to spin out their ideas into continuing sustainable businesses. So the kind of conversation we're having here with folks such as yourself, I think it's important to raise your awareness that these kinds of technologies are actually being incubated by RPE, and that it would be, I think, quite interesting for us to get a sense from you on whether you would like to learn more about any of these. So I would be happy to introduce you to the teams that are actually doing the work.
Great, thanks, Chris. I think that really links it to the specifics of how to connect up with investors and other partners in moving this forward. So let's see, Peter, yeah.
Yeah, so Mark and Krishna, excellent presentation. Thank you so much for pushing that forward. Let's see, several questions. One is the slide deck available? Real quick.
Yeah, we can make that available.
Great, okay, good. Yeah, send that maybe to Paul and he can forward it. I've been working closely with Brian von Hertzen, who's of course been working on the macroalgae for a decade or so, and now C Combinator working on the processing side. The question I have is, who is doing an overall project plan for this? That is to say, the macroalgae does grow. There is a market for it. Who's looking, do you have anyone looking at how do we synchronize all the players so that the thing just succeeds? Research is important, but nature has proven that these things happen. So now it's a matter of synchronizing the parts. And do you have anyone working on that?
Yeah, I don't know quite synchronizing. I think one of the things that we have been doing, I think what is unique about the Mariner team is that when we launched the effort about 5 years ago, other than a few artisanal farms, there wasn't much that happened in the US. And so besides funding specific technology developments, I think the major contributions that a program like the Mariner has been making in the US is bringing together a community. So what we typically do is we have annual meetings, so that where we not just bring all the performers together to exchange information, but really bring in external stakeholders as well to enrich the conversation, to grow the community. And I think then raising questions beyond the individual technology. And so big questions are, it's like, what are the next markets? And so this is something that we actively address, but ultimately, since we are only a starting point, hopefully the legacy is a vibrant community that will carry this technology and this space forward. And so I think there's not a central planning committee, but there's really more the idea of looking into the future. How do you support the growth of a community that then carries forward?
That's great. I love how that acknowledges Paul. So Paul Holthus, thank you for doing that orchestration work.
Well, I would just say, Mark, on that, and I don't want to take up time from others who want to intervene here, but in that sense, we should be talking about how to build on the great work that is going on here, and it relates to what we'll be talking about in a few minutes on the Phytoplankton Council idea to think about the macroalgae community in terms of CDR and ocean restoration, and the need to continue to have that community, particularly again from the business and investment side, especially interacting with each other and advancing the game overall after the Mariner program is wound down. If I understand correctly, that it has a time limited capacity and plan, but let's make sure we don't lose the momentum and the community that you guys have done such great work to develop. So if we can help in that way, that's certainly the sort of thing that the platform that the World Ocean Council is here to provide for the business and investment community.
And that's what we are really looking to engage organizations like yours. And we have been engaging the algal biomass organizations that comes more out of the microalgae space, but has clearly been branching into the macroalgae as well, because you really need representations on various levels of professional organizations. And once again, this is intersecting with a lot of different technical and commercial communities. And we want to make sure that it gets rooted in quite a number of those.
Yeah. Other points that people want to bring up, please.
Yeah, hi. Christoph Harwood. We from Simply Blue. We are project developers. We develop floating wind offshore farms. We develop wave energy. We're looking developing low impact salmon farms. How long do you think it is before it will be ready for us to develop floating algae, macroalgae farms to capture carbon? Are we looking 5 years, 10 years? I mean, there's technology readiness, and then there's policy readiness, and then there's market readiness. So should I just file this away for future use, or should we start looking for sites now?
The flippant answer would, considering how long it takes to get a permit, you better start now. So, but
yeah, I mean, it takes us 10 years to do a wind farm. So,
well, then you are actually, I think you might have the right time horizon. Once again, we don't know yet how long it takes. A lot of our teams on a research level have been taking 1 or 2 years. Turns out that Alaska is actually very proactive, and so they were able to a 25-hectare farm took them, I think, just over a year to permit. And I think the biggest challenge right now is to really drive forward the business model and then find the right stepping stones. It's like, if you cannot expect that we have this $80 a ton target in 2 years. There's just, I think we have to go through a learning curve to drive costs down. But if you find initial higher value products, and this is why we look at feed markets, for example, as an alternative. So I think there are real ways of starting to look at ramping this up and looking creatively, partnering it with other opportunities.
Yeah, I mean, it's interesting at the moment, if you look at things like wave energy, it might be 5 times more expensive than offshore wind. We're happy to go in early as long as we have the right government support to do that. So we're not too nervous if it's expensive at the start. We just need to see a journey that it's going to come down to the right area, and there needs to be policy support for that.
Since this group is focused on carbon dioxide removal, I think it would be interesting to compare the potential of macroalgae from a cost and volume point of view with some of the other solutions that are being bruited about. And I think from that point of view, certainly I would look at the potential for macroalgae as being very much in the competitive space, both from the point of view of what's possible now versus what's possible to scale in the future. There's nothing today that we see from a high volume carbon dioxide removal point of view that's going to get you into these kinds of cost regimes without really a lot of learning and a lot of scaling in the future. So I think really the question is, what's your horizon versus your goal? And as Mark said earlier, with all of these, the question of validation and how you define permanence of carbon capture becomes a very important question. Those are some of the things that we certainly are grappling with now and trying to answer. But I think that the space has a lot of potential for the standards development and quantification methods that allow you to compare apples and oranges to really get to where the claims that people are making can be objectively verified against a landscape of different technology options.
Yeah, thanks, Chris. We'll go to Phil. I'll just mention though, Mark, really good to highlight the spatial management aspect. And this is something personally I've been involved for decades on what's now being called marine spatial planning. And then Chris for bringing up the co-location opportunities here of wind and aquaculture, and wind and aquaculture that could be then linked to CDR and restoration. And so I think these sort of spatial management and industrial synergy aspects are really important parts of the scaling opportunities here and the economies of scale in terms of getting permits and so on. Phil.
So, Mark, I'm just curious on the marine operations. I know in my own project, I struggled with 2 sides of that equation. One is the cost of operating a boat far offshore, or even not so far offshore. Boat costs are very expensive, and the CO2 footprint of a workboat or a large vessel is also pretty substantial. So, have you taken a look at how far offshore can you really go without running into those constraints? A, the marine vessel cost, and B, the CO2 emissions of the marine vessel that effectively kills your CO2 drawdown or sequestration.
Yeah, so we asked all of our teams as we structured the program in a phase 1 and phase 2 part, where in the initial phase 1, we asked them to primarily work on the conceptual design, an engineering analysis, but also a techno-economic and LCA type analysis, where they should look at an operations plan and see how you are able to meet the goal of at least 5-to-1 energy return. And you're absolutely right that very energy efficient harvesting is critical. And then the other part is really how far you transport it. So, and our conclusion has been that we haven't really looked yet at the exact number. It will be different from operation to operation. But once you get past 20 nautical miles, 25 nautical miles, you may have to look very closely at offshore processing, actually, that you don't take a vessel back and forth all the time. We have had some elements and this green, the yellow vessel that I showed was looking at an autonomous vessel that goes at only 1.5 knots to minimize drag and thereby being very energy efficient. And at the same time, autonomy is critical there, because people would go nuts if they were sitting on a boat that goes at 1.5 knots. And so that also you couldn't pay for the staffing of a vessel like that. So, but you're right, it's something that we need to look very, very carefully at. The vessel costs are really high, and operationally and investment wise. And so, for example, in Alaska, one of the things that we have been looking very closely is how can you dual purpose the whole fishing boat fleet in Alaska that sits dormant most of the winter. There's really actually a good complementarity with the periods when they use it for fishing and when they could use it for seaweed farm operations. And so it doesn't yet save you any fuel, but at least it saves you some of the vessel costs.
Interesting stuff. And okay, one more comment from Peter. The time always goes so quickly in these, and I hope you all agree that the value of these roundtables is to be able to have the time to get into these discussions rather than just quickly move on. So we have a longer agenda than we've had time for today as usual. I think that's a good thing. So we'll take Peter's point, and then I do want to make sure we at least cover the Phytoplankton Council and touch very briefly for next time to talk then about the COP26 and starting the ball rolling on that discussion. So Peter, go ahead, and then we'll move on to the Phytoplankton Council.
Yeah, Mark, this was an interesting topic regarding distance from the shore. And you were focusing on the US EEZ. Are there limitations to working outside of that in internet? Besides just the distance and
I think there's somewhat different regulations or lack of regulations that may play a role. So I don't see that if you're 190 nautical miles versus 300 nautical miles, I'm not quite sure that there's dramatic differences. I'm not an expert in the laws of the sea that I could really tell you, and Paul might know a lot more about that than I. But we just, as a US agency, we focus on US waters because there we have the highest degree of control. That doesn't mean that these solutions are limited to the EEZ.
Great.
Yeah, and I think this is a big part. The political and social license are going to be a big part of this, as with the other pathways to ocean CDR, and certainly need to be worked on as part of that spatial management as well. And something Phil also, I think, and for the other systems, just that organizing who all is using what part of the ocean and how we manage these things is going to be critical to scalability. So some really, big, important and fundamental things to be worked on there with other, with other entities and stakeholders as we work to drive forward with enterprise development and investment opportunities. So thanks again, Mark and Krish, and if you and Phil agree, we'll make the presentations available, and certainly the recording will be available, and transcript from the session today. We've got 10 minutes or less left on this. I would like to introduce the next item and then pass it over to Peter to elaborate on a bit. And this is what we've started to call the Phytoplankton Council. So we're seeing, as has already come up regarding macroalgae, communities of practice, either within just the more private sector side, but also multi-stakeholder communities emerging around the different pathways, if we use that terminology, for ocean CDR. And one of the parts that's starting to come together on that hasn't sort of had a home or a sort of catalyst and facilitator is around what we're calling the phytoplankton community or phytoplankton council, with people like John Ridley at Ocean Nourishment and others. And so we're seeing and having positive feedback from people involved in that space that there would be value in being able to work together and really develop and drive forward that approach to carbon dioxide removal. So Peter, do you want to elaborate on that a bit? And I think Phil, this relates, of course, directly to what you guys are developing as well.
Yeah, thanks. So the idea for this came in a couple discussions I had with John Ridley. And I think pretty much everybody on the call here is familiar with the John Martin 30 years ago talking about how the ocean absorbs most of the CO2 between ice ages. And there's a big capability. And of course, there's been a lot of controversy over the last 10 or 15 years. And as I've talked with lots of people who've worked with John Martin and people following him, there's a lot of fear. And so the first idea is to just get a group together who's saying, listen, we're committed to utilizing nature's pathway for microalgae, both to restore the ocean, to restore whales and CO2, and sort of a strength in numbers idea. It also would provide, it would be an informal group with taking no actions, no positions, no commitments, wouldn't be funding anyone, we don't think. But would also be a place where if someone's writing an article about ocean CDR, they could actually find people who have been involved in various phases of phytoplankton CDR, and the whole gamut of it, not just the kind of things that John Martin wrote about. It also would be a place where people have questions, they can answer it, where articles can be posted. So if someone wants to know, tell me about about that whole field, then say, here's a bunch of articles that have been written by experts who've done it. And so I just wanted to share that idea and also see who, if anyone, might be interested in joining it. I asked Sir David King if he'd join it, and given his prestige, and he said yes. So we actually have a little bit of momentum here to get started with. Paul, yeah, Philip, go ahead. Oh, you're on mute.
I just said, sign me up, Peter.
Okay, good.
Yeah, obviously, highly interested.
Great.
Salvador, did you want to add in?
No, also that I'm also interested in being part of that.
Great.
Great. And I know, Mark, you mentioned how some of the microalgae folks that were starting to kind of get into the macroalgae, but certainly if there's folks that you're aware of, and anyone on the call here aware of that would be valuable for us to reach out to. And I see Francisco is saying he's interested as well.
Right.
So, and we can put out broader information on this as it gets going, and it's really to facilitate this community of practice, and as Peter was saying, and really help create a momentum around this. And as we were talking earlier, there's similar efforts underway with the macroalgae community, and we may, if we can be assistance with that as well. But this is a sort of coalescing and creating momentum that I think people are interested to see happen. I see Andrew's saying he's interested as well. Mark, did you want to say something there?
Oh, great.
No, it's like I'm happy to make a connection to ABO in that space, but the only thing that they are looking more of cultivating specific species as opposed to broadly supporting phytoplankton, so which is clearly a little bit of a different approach. I'm not quite sure how much overlap there is, but there may be some underlying knowledge exchange that might be beneficial.
Great.
I missed ABO.
The Algal Biomass Organization.
Right. So they're looking at cultivating specifics.
Yeah, they are the
micro.
They have done a lot of algal cultivation broadly, but it started a lot back in 2008. They called it the Summer of Algae, and that was very much focused on cultivation of microalgae.
Got it. Great.
Right. I remember all that activity then, and U.S. Navy and others working on this. And
I'd also like to volunteer to get information on this Phytoplankton Council. I'm not sure I could devote a lot of time to it, but I'd love to. Thank you.
Great.
Thanks very much, Ross. Would be, and a part of it will be as Peter was saying, a way for people to keep informed sort of passively by being part of a network. So good. Well, great to see the level of interest in this just from the group we have on the call here. So Peter and I and John Ridley will be moving that forward and getting an initial group together as soon as we can. And again, John unfortunately was traveling today and couldn't join us. That being John Ridley from Ocean Nourishment, who spoke and presented their work and their company last call of this group.
Yeah, so I'll have a little bit of a one-pager about it. And yeah, it's definitely, the idea is just a place there's strength in numbers, no positions, no work to do, Ross. You don't have to do anything, just be part of the community.
Yeah, very good. In the 2 minutes we have left, I'll just introduce this point then that, well, just the point then, the COP26, the annual UNFCCC gathering around climate change, which has increasingly had an ocean focus the last several years. World Ocean Council is an accredited observer, and I've personally been involved in, as I was mentioning before the call started, been involved with the UNFCCC and this sort of stuff for many decades. So we're working with other colleagues on how the ocean restoration CDR community can be best involved there, and making sure that we're getting the sort of the strength in numbers approach to this, because this is an increasingly developing and complex community. And so we've already had some initial discussions with Climate Works and Ocean Visions, and Brad had to drop off the call, but certainly Ocean Visions, which has invited me to be on their leadership council, so that we really develop close relationships and working areas with them to bring in the more multi-stakeholder approach. But we were really keen to make sure that the business and investment aspects and angles of ocean CDR and restoration are part of what gets put in front of everyone, particularly governments, and especially hopefully at a high-profile, high-level event at COP26. And so let's pick that up, and really wanted to brainstorm that a bit through the roundtable to get people's thoughts on what what might be some of the best ways to do that. And I'll just in the last minute here just highlight that Andrew Smith from Greenbackers is based there in Glasgow, and so we are already also talking about what kind of physical facilities and meeting space might be available and so on, and what kind of agenda for the ocean and ocean business development and investment in particular to be pursuing there in Glasgow. I don't know if, Andrew, you wanted to make any comments on the situation.
Well, nothing too long at this stage, but just to say we are indeed in Glasgow, and we are putting on our own event during the COP there, but very happy to talk about that further and be boots on the ground for anybody on this call or anybody else who's a member of WOC, a sounding board, a guide, happy to help in any way at all.
Great, and hopefully we can stay at your place, Andrew, given the limited accommodations at Glasgow.
Yeah, very reasonable rates, no problem.
Okay. All right. Well, look, we're over the 90-minute mark here. I want to really respect everyone's time. Thanks, Phil and Mark and Krish, for great presentations. Thanks all of you for great discussion. I hope you're feeling this is valuable. We'd like to dive in a bit deeply on things, and the 90-minute time slot seems to be a good amount of time. And we'll be, as I said, working to set a set date every month, so we can make it easier to people to plan ahead for these gatherings. And we'll be making the outputs and the presentations available to the overall group as we move forward. So with that, I'll close off and thank everyone, and let you get on with your evening or day or morning, wherever you are. Take care.
Thanks very much, Paul. Thanks for brilliant presentations for those guys that did them. Thank you very much indeed.
Yeah. Thank you, Paul.
Thank you very much.
Mark.
Thank you all, folks.
Thank you all. Nice to meet you all.
Thank you very much. Bye-bye.
It was very interesting. Thank you so much. All the best.
Thanks, Rafa. Thanks a lot, Phil.